Science is real, from the Big Bang to DNA. Science is real, from ever.
Soil is comprised of solids, liquids, and gases. In our studies, we are interested in the upper soil layer, the one that we are most likely to interact with. As you would expect, the chemical characteristics of a fertilized soccer field are different than those of a streamside forest or a sandy beach. In this investigation, you will test samples that are mostly sand and others that are mostly clay. These samples have been dried, leaving the mineral and organic components. Sandy soil often contains a great deal of the mineral quartz. Quartz has the formula SiO2 and is called a primary mineral. Clay soil is usually a mixture of different secondary minerals. Some of the clay samples you will test are mostly the mineral kaolinite, shown here. You will also have samples of the mineral vermiculite, which is shown here. The properties of sand and clay are quite different. Consider what happens when water is added to these different soil samples. Obviously, the flow of water through sand and clay is very different, passing quickly through the sand but slowly through the clay. How can this dramatic difference be explained? You will begin by describing the physical texture of sand and the clay minerals kaolinite and vermiculite. To address the overall question of why different types of soil interact so differently with water, you will conduct several investigations. In Part A, you will consider whether the size of the particles in a solid affect the amount of empty space in the solid itself. Or perhaps water sticks to clay minerals more readily than sand. That will be investigated in Part B. In Part C, you will consider whether the void space or the empty space is the same for sand and clay minerals. In Part D, you will continue your characterization of sand and clay minerals by considering which one provides more ions to an aqueous solution. And finally, in Part E, you will work to characterize how much clay is in a particular sample. Let's look more closely at each of these research questions. In Part A, you will investigate the idea of void space. The void space in a solid is the percentage of the volume that is empty, filled with air. Your objective here is to design experiments to determine the void space for different spherical objects and determine whether it depends on the particle size. An important resource for Part A are different sized objects, all spherical. Please pick up these resources at the front of the lab. Be careful, because they will roll around. An important characteristic of water is its polarity. Does water's polarity cause it to stick to the clay minerals? In Part B, you will design experiments to determine whether a liquid's polarity affects its flow rate through sand and through clay minerals. Notice you have 3 different solids to test and also 3 different solutions. This leads to a total of 9 different containers that you can test all at the same time. In Part C, you will move on and design experiments to determine the void space for sand and clay minerals. You will have the sand and clay minerals and also the methanol and dichloromethane. Use 50 ml of sand, kaolinite, or vermiculite in a particular test. Do not discard the solid. It can be reused. Our overall research project is based on understanding how ions interact with soil. How can you test whether ions are in a solution? With a conductivity sensor. As you have probably seen, deionized water does not conduct electricity. However, if a strong electrolyte is added, like NaCl, the light bulb goes on. A conductivity probe reports a small number for a solution that is a poor conductor, and a larger number for a good conductor of electricity. You will use such a conductivity probe to test various provided solutions. Much of this experiment has involved a comparison of sand versus clay minerals. How can you determine the amount of clay present in a particular soil sample? This question is addressed in Part E. Clay minerals result when primary minerals, like quartz, are transformed into secondary minerals. The extent to which this occurs may vary for different soil samples, since they may have experienced different degrees of weathering. It turns out that the amount of rubidium in a sample is proportional to the amount of clay there as well. In Part E, you will measure the amount of rubidium in soil samples with an X-ray fluorescence spectrometer and use this information to calculate the amount of clay the samples contain. The XRF spectrometer is a remarkable instrument that rapidly determines the elemental composition of a sample. Your teaching assistant will assist you when using the instrument. What are the keys for success in this lab? Obviously, there are several parts to this experiment, but all of them may be completed fairly quickly. You will have plenty of time to think about your results, to make sense of them, and to see what they mean. This is a group project, so everyone in the group must contribute. Do not sit to the side and rely on your classmates to complete the lab. Participate.